2.6 Related Rates, Example 4. A balloon rising from the ground at a rate of 140 feet per minute is tracked by a rangefinder at point A, located 500 feet from the point of liftoff. Find the rate at which the angle at A and the range R is changing when the balloon is 500 feet above the ground. So, we have a point of liftoff for the balloon going straight up. This I'm going to label as the height of the balloon. Now, 500 feet away from point of liftoff, we have a rangefinder. Because the point of liftoff doesn't change, and we're not going to be moving the rangefinder around, this 500 is a constant. Therefore, I'm going to go ahead and label that on my picture. Now, the range R is talking about the distance from the balloon to the rangefinder. So, we were given that the balloon is rising at a rate of 140 feet per minute. If the balloon is rising at a rate of 140 feet per minute, that is the rate of change of the height with respect to time. Now, as the balloon is lifting upward, that means that this height is increasing. If the height is increasing, that means that the rate of change of the height will be positive. Now, we're trying to find the rate at which the angle at A and the range R is changing when the balloon is 500 feet above the ground. So we are looking for the snapshot of 500 feet. The first thing they ask us is to find the rate of change of the angle. So I'm going to label the angle here at A and say we're looking for d theta dt. In order for us to find d theta dt, we need to come up with an equation that relates theta with the other information in our picture. Now, remember that we were given information about h. So when I set up my equation for theta, I want to make sure that h is in there. Since this 500 is a constant, it's a lot easier to work with this than it would be another variable. So I'm going to set up a formula that relates theta with its opposite and adjacent side. Opposite and adjacent side is a tangent relationship. So I'm going to say that the tangent of theta is the opposite side, which is h, over the adjacent side, 500. Now, to make this a little friendlier to look at, I'm going to multiply both sides by 500 and then take the derivative. So the derivative of 500 tangent theta will be 500 secant squared theta d theta dt, and the derivative of h with respect to time is dh dt. Now, looking back up at our givens, we know that dh dt is 140. We know that we're trying to find d theta dt, but the question is, how do we find secant squared theta? Now, the trick to this is to recognize that we don't actually have to know the angle measure to find this. All we need to know is the secant of the angle. Now, if you remember back from your pre-calculus days, the secant of theta, the secant of your angle, is going to be your hypotenuse divided by the adjacent side. So if I can come up with the hypotenuse and the adjacent side, I can come up with the secant value without even knowing the angle measure. So at the snapshot of 500, I can use Pythagorean theorem to figure out what that range is. So 500 squared plus 500 squared, and then take the square root to find that range, we end up with 500 times the square root of 2. So that means that the secant is going to be the hypotenuse, which is 500 square roots of 2 divided by the adjacent, 500. And that simplifies to the square root of 2. So now let's come back down here. We have 500 times the secant value, which is the square root of 2, squared, times d theta dt. Now, the square root of 2 squared is 2. 2 times 500 is 1,000. And then we can divide to solve for d theta dt. So d theta dt is 140 divided by 1,000, and that reduces to 7/50. Now, let's go ahead and talk about the units. Our angle measure. In calculus, angle measures are always in radian. So, radian measure, and then once again, we're talking with respect to time, in this problem, is minutes. So, the rate of change of the angle is 7/50 radians per minute. Now, they asked us another question. They asked us to find the rate of change of r. So we also need to find dr dt. So once again, I'm going to go to my picture, and I'm going to find a relationship between r and the other information on the picture. Although there's a lot of different formulas that you could come up with, probably the one that most people would use would be Pythagorean theorem. So we can say that 500 squared plus h squared is going to equal r squared. Notice I have not plugged in the 500 or the 500 square roots of 2 because the h and the r are variables. They are changing. So we need those in there until after we take the derivative. Now for this one, 500 squared. 500 is a constant. A constant squared is still a constant, and the derivative of that would be 0. The derivative of h squared is 2h dh dt, and the derivative of r squared is 2r dr dt. Now I can come in here and I can divide both sides of the equation by 2. So h dh dt is equal to r times dr dt. And then come up here to our givens and fill those in. At the instant in time, we have 500 for h. We have dh dt as 140. R is 500 square roots of 2, and dr dt is what we're trying to find. So, when we divide both sides by 500 square roots of 2, the 500s actually reduce, and we get dr dt is going to be 140 over the square root of 2. Now, for units, we know that the range, r, is measured in feet, and the time in this problem is measured in minutes. So the rate of change of the range with respect to time is 140 divided by the square root of 2 feet per minute.